These two sections, 5.1 and 5.2, are really review sections. So we talked a lot in the algebra classes about logarithms and exponential functions. So we're just going to review some of those, the main topics from logs and exponentials today. So starting out with kind of a definition. So the reason that we needed this log function was because, say we started out with, here's some equation written in exponential form. So what if we needed to solve that equation for y? So to do that, that's where we had to define a new type of function, the logarithm function. So here we would read this: if x equals b to the y, then y equals the logarithm base b of x. So this is the corresponding logarithmic form. So the way I like to remember this one, I like to think of this one as, if you look at the logarithmic form here, you'll see that the y corresponds with the exponent from the exponential form. So I like to read that equation. The exponent is the log. Now you see the base of the log corresponds with the base of the exponential. And then I just say of the other side. So that's just kind of me translating this equation into something that's kind of easy to remember. So if I look at a few examples, let's just start with changing the form. So that would be changing from exponential to log form, or vice versa. So I don't know, I could start with something like, let's see, x equals 4 squared. So that guy is in exponential form. So I'm looking kind of up here and I'm going, okay, this guy is written in exponential form. So I'd like its corresponding log form. So I'm really translating using this rule I've written here. So I'm going, the exponent 2 is the logarithm, the base is 4 of the other side, so of x. And so I've written that in log form. So how about something like, I don't know, 1/25 equals 5 to the negative 2. So again, I'm in exponential form. So to change to log form, I'm looking again at this rule here. So I'm going, the exponent, negative 2, is the log, this would be a base 5, of the other side. So of 1/25. So there's that written in logarithmic form. Okay, how about if I start with something in log form? Something like that, say. So my goal would be to write this in exponential form. So that's actually even easier. So look, this is the base. This is the exponent. So it'd be, let's go with my other color, it'd be 2 to the third equals, and then the only thing left is the 8. So there's that guy written in exponential form. Here's another one. How about log base 3 of x equals 14. Okay, so changing into exponential form, here's the base, here's the exponent. So 3, should I use my black, 3 to the 14th equals x. special logs. So the first one is we say, okay, so if we have a log, bet you remember this one, and it's a base e. The way we write that is instead of writing log base e, we write ln of x. And that stands for the natural log. That one's called the natural log of x. The other special one is if I have y equals log base 10 of x, we write that one as just log of x. So in other words, it looks like it's a logarithm without a base, but that's because we're assuming that you know the base is 10. So that one's called a common log. So those are my special logarithms. So you'll remember from algebra, remember this e, what is that? That e is approximately 2.7. And that's just an irrational number. It's called Euler's number. Okay, so let's see. So if I go back up here and add a couple of problems to this list, what if I have something like, 5 equals e to the x? My goal is to change the form. So again, I have an exponential. To put this in log form, I'm thinking the exponent equals the log base e of the other side. But then this time I go, well, I recognize this one is a special one. So as my final step, instead of writing log base e, I'm going to write ln of 5, the natural log of 5. How about if I have something like x equals 10 to the 4th? Okay, so in log form, the exponent is the log base 10 of the other side. And again, I recognize this one as a special log. This is the common log. So I'm going to write this as 4 equals log of x. Okay, what if I start out with x equals ln of 4? Okay, so now I have a logarithm, because remember I could write that equivalently as log base e of 4. So to change this into exponential form, I'm going the base to the exponent equals what's inside. So in other words, this would be e to the x equals 4. Number 8. How about 2 equals log of x? Okay, so to change this into exponential form, first thing I notice, this is a common log. I know I'm to assume the base is 10. Okay, so that it's going to be 10 to the second equals x. All right, so what I've done there is I've worked on changing between exponential and log form. Okay, so what are some other things that I could do? So what about solving some equations? Okay, so what if I wanted to solve, how about something like e to the x minus 4 equals 0? This is very easy. So if my goal is to solve, that means I need to isolate the x. So I would start by adding the 4. Okay, then again, in order to isolate the x, because that x is in the exponent, I'm going to have to change to log form. So I'd go, the exponent is the log base e of the other side. Then I recognize again log base e, we denote that as ln, common log. So there's my answer. All right, what about something like that? Looks a little bit more interesting. So with that one, I noticed that I have a common factor, a GCF, e to the x. I'm going to start by factoring that out. So what would that leave me? An x minus a 3? E to the negative x. So let me double check if I distributed this through. I'd have x e to the negative x, that's this, minus 3 e to the negative x. So that looks like I factored that out correctly. Okay, so now I'm looking at each of these two factors and I'm going, okay, well, if I multiply these two factors together and the result is 0, then it must be true that either e to the negative x is 0 or x minus 3 is 0. So if I attempt to solve this first one, I go the exponent is the natural log of the other side. But actually, if you remember from algebra, I can only input a positive number to a logarithm. In other words, I actually cannot take the ln of 0 or the ln of a negative number. If you look back at this line, it kind of makes sense because we're going to look at reviewing graphs in a minute, but if you remember what the graph of, say, e to the x looks like, well, an exponential function is never going to be less than or equal to 0 because that graph has the horizontal asymptote at 0. Now, this guy's been reflected, but still, looking here, e to any power is not going to give me 0. Okay, so in any case, I know that this guy is impossible. So that does not contribute any solutions. So in that case, my only solution then would be x equals 3. What about for number 3, something like 4 to the 3x equals 4 to the 6th? So here we have an exponential equation. Actually, we have the same base on both sides. So the only way it's going to be possible for these two quantities to be equal is going to be, well, if the exponents are also equal. So we would conclude that 3x has to be equal to 6. Therefore, the x must be equal to 2. With something like number 4, we actually have a common base because both sides of this can be written in terms of base 3. So that's going to be the route that I go. So I'm going to leave the left side as it is. That's already in base 3. The right side, I'm going to say, well, let me see how I would write 1/9 as 3 to a power. That would be 3 to the negative 2, right? And then here I have power to a power, so I would multiply the exponents. That'd be negative 2x plus 2. Okay, So now I have the same base on both sides. So again, I would conclude that the exponents must be equal. So negative x plus 2 must be equal to negative 2x plus 2. Let me combine the like terms. Let's see, I can subtract the 2's and add a 2x to both sides. So what do we have? 2x minus x is x, and that leaves me with a 0. So I guess my x would have to be 0. Number 5, I actually have a common base as well. And this one is base e. So let me see if I can rewrite these. So 1 over e to the negative, or 1 over e to the 2x, isn't that the same as e to the negative 2x? And then square root is the same as power 1/2. Look like that. Again, power to a power, multiply. So e to the negative 2x is e to the 1/2 x plus 1/2. Okay, and now would conclude again that my exponents must be equal because I have a common base. So negative 2x is 1/2 x plus 1/2. And then solve. So I don't know, maybe should I multiply this whole equation by 2? Then what would I have? Negative 4x equals x plus 1. Negative 5x equals 1. X equals negative 1/5. So number 6, this is a special form. This is one we would call quadratic in form. Because you see how this kind of looks like a something squared plus a 2 times a something minus an 8 is 0. So wouldn't my u be e to the x? This is a substitution. So if you think about it, look, so if I have e to the x squared plus 2 times e to the x minus 8, here I have power to a power, so I multiply, right? Okay, so look, isn't this my u, so u squared, and then plus 2, and then here's my u again? So that's how I got this equation. So actually, that's going to be really easy to factor. So let me see. So how would I factor this in u? So that'd be u. Let's see, u plus and u minus 4 and 2. Now the thing is though, remember I'm not solving the equation for u. I'm actually solving the equation for x. So I actually need to go back and back substitute. So what I actually have here is either e to the x is negative 4 or e to the x is 2. So this one's impossible, right? E to the x can't be negative, or in other words, I cannot take the log of a negative number. This one, though, I can solve for x by changing to log form. So there's my solution. Okay, what about a number 7? So I would start something like this by clearing the fraction. So 30 equals 10 times that denominator. So then let me divide by 10. 3 equals 1 plus 2e to the negative x. 2 equals 2e to the negative x. Divide by 2. E to the negative x equals 1. So negative x equals ln of 1. So what the heck is ln of 1? So ln of 1, remember what that's saying? That's saying e to what power equals 1? E to what power equals 1? Well, isn't e to the 0 equal to 1? So wouldn't ln of 1 have to be 0? E to the 0 makes 1, right? So isn't this saying negative x equals 0? Or in other words, x is equal to 0? All right, so what about some of these where I need to use log properties to expand? So I guess I need to actually write out some of those log properties. Let's start that list here. So these should look familiar. So if I have a log with any base of a product, I can break that up as the sum of two logarithms. If I have the log of a quotient, I can break that up into the difference of two logs. If I have a logarithm with a base m and an exponent r, I can actually bring the exponent down to the front as a multiplier. So r times the log base b of m. So those are the main log properties. There are a few other ones I can add to that list, but those are really the most important. So if you're looking at something like example 1 here, notice that I have the log of a product. I have this guy times this guy. Now I do have an exponent, but notice that that exponent 3, it's only on the one factor. So I can't actually move that to the front of the whole logarithm because it's not attached to this first factor x squared. So instead, I'm going to first use the fact that I have a product, and so I'm going to use rule 1. Okay, so this turns into the log of x squared plus the log of x squared minus 4 cubed. Now I can bring the exponents down. So then I have 2 log of x plus 3 log of x squared minus 4. So that looks pretty good, but then I notice that x squared minus 4 is actually a special form. That's a difference of squares. So whenever I see that, I think, well, maybe I should try factoring that. That factors as x plus 2, x minus 2. Because then you can see I actually have another product here. So can't I then use my sum rule again to break that into the sum of logs one more time, squeezing that in there. So let me distribute the 3. So I'd have 2 log of x plus 3 log of x plus 2 plus 3 log of x minus 2. And then I'd be done. So how do I know when I'm done? Well, I really have rules. I have 3 rules to look at. I have one rule for if I have a product or a quotient inside of a log or an exponent inside of a log that I can bring to the front. So looking at my expression here, inside these logs, I do not have any products, quotients, or exponents that I can bring to the front. So I'm done. What about something like number 2? So number 2 is a natural log. I can use all the same rules. So I'm going to start by saying, okay, well, again, I can't bring either of those exponents down. They would have to be here, say, in order to bring that down, because that would be an exponent on the whole expression. So instead, I'm going to use the fact that I have a quotient. Okay, so I guess I'm using second rule up here. There we go. Okay, so I'm going to have ln of the top minus ln of the bottom. Okay, and then what next? So here I have a product, right? Here I have another product. So let's see. First term's going to turn into ln of e cubed plus ln of x squared. I'm going to have ln of square root of x plus ln of 3 plus x squared. Then what else? I can bring the exponents down here. 3 ln of e plus 2 ln of x minus ln root of x minus, should I bring that 2 down? Ln of 3 plus x. Okay, can I do anything else? So what is ln of e? Okay, this is saying e to what power is e? Well, that's 1, right? E to the 1 equals e. So isn't ln of e just 1, 3 times 1? And then what about this one? Square root is exponent 1/2, right? So I can bring that down. Okay, and then let's see. So I'm looking inside my logs for multiplications, divisions, or exponents. I don't see any of those. Let's see, is there anything else I can do? Well, I noticed that actually these guys are like terms. Those are both ln's of x. So let's see, I have 2 ln of x minus 1/2 ln of x. So isn't that 1/2 or 3/2 ln of x? Look like that, right? about going in the opposite direction? So maybe I'll make this one. Let's make this one a y. So combine into a single logarithm. So I have 3 ln of x plus 4 ln of y. So I guess the first thing I would do would be I would bring these coefficients up as exponents. So I'd have ln of x cubed plus ln of y to the 4th. And then, because I have the sum of 2 logs, I can change this into a log of a product. I multiply the arguments. Start number 2 the same way. Moving the exponents, moving the coefficients inside as exponents. Let's see, it's going to be ln of x squared minus ln of y cubed plus ln of z to the 4th. Okay, let's see. So here I've got a subtraction. It's going to turn into a quotient. And then I've got a sum. Okay, so what I'm going to actually have here is I'm going to have a product like so. Should I write the last step here? So ln x squared z to the 4th over y cubed. So there's something that you can kind of notice with these. It'll be helpful in our last example. So let me see how the best way to point this out would be. See if I can clean this guy up a little bit. Okay, so if you look at the completed combined logarithm here, the fraction, see how in the bottom of the fraction, the only thing in the bottom of the fraction is y cubed. So if you look back at the original equation, see how the y was the only term that had a negative in the front? So this negative coefficient actually means that the argument of that log is going to end up in the bottom of the fraction. Versus if you look at these other two terms, this one and this one, you see how they started out with positive coefficients, positive and positive. So both of those ended up in the numerator. So actually when I'm looking at this last one, this looks really ugly. Let me start it out. I mean, the first thing I would do regardless is I would move the exponents, coefficients in as exponents. So what does that give me? I've got ln x squared y to the 4th, z, and then to the 3rd, minus ln x to the negative 4, y, z to the negative 2 squared, minus ln y to the negative 3, z to the 6th to the 5th. Power to a power, I multiply, so I'm going to have x to the 6th, y to the 12th, z cubed. Then I'd have, what, x to the negative 8, y squared, z to the negative 4, y to the negative 15, z to the 30. Let me double check all these. X to the 6th, y to the 12th, z cubed, x to the negative 8, y squared, z to the negative 4, y to the negative 15, z to the 30. Okay. So then what next? So then the thing is this. Well, you see how I have a negative here and here? And I have a positive here, so it's positive, negative, negative, right? So actually, what does that tell me? Well, that tells me, I can put a fraction together here. I just need to figure out what goes in the top and what goes in the bottom, but that's very easy. Because only this term with the positive coefficient, that's the only term that's going to contribute to the numerator. So I'm going to put the arguments from that term in the numerator versus the other two terms here, this guy and this guy. Those both have negative lead coefficients. So the arguments from those logarithms are going to go in the denominator. That makes it a lot simpler. And then I just have to simplify using exponent rules. So let's see. Let's look at that denominator. I guess the numerator's already simplified for now. So what do we have there? We've got x to the negative 8. Oh, I guess that's the only x. Let's see, we've got y squared, y to the negative 15. So that's what, y to the negative 13? And then what else do we have? We've got z to the negative 4 and z to the 30th. So that'd be z to the 26th. Okay, now I'll look at the variables. So let's see, I can move that x to the negative 8 up as x to the positive 8, right? So what would I end up with there? Looks like it'd be x to the 14th. Okay, and then look, I can move this y to the negative 13th up as y to the 13th. Then I'd have y to the 25th. And then my z's, let's see, I can cancel 3 to leave me with 23 in the denominator. Should I clean this guy up a little? And so I think got everything right there. So what about just a couple of graphing questions? I don't want to go into too much detail with the graphing, but I do want to look briefly at graphing. Say this is the natural exponential function. And then here is its inverse, which is the natural log function. So I bet you remember what this exponential function looks like from algebra. You should. Something like that. But actually, exponential functions are really nice to graph. Let me see if I can set up a nice coordinate plane here. Something like that. Okay, because I can actually just do a little table of values. We even just put a couple of values in here. Okay, what's e to the negative 1? Well, that's 1 over e. Okay, that's 1 over, well, so let me say approximately 2.7, right? So, I mean, that'd be pretty close to like a third. So let me see if I can plot that point. I mean, it'd be right here somewhere. I can even label it negative 1, 1 over e. E to the 0 is easy. That one's 1. It's here. E to the 1. Oh, well, that's about 2.7. So it's right here. Now, I know if I was to continue plugging in smaller values, like if I continued this table, I'd have e to the negative 2. That's 1 over e squared. Negative 3. That's 1 over e cubed. Negative 4. 1 over e to the 4th. So what I'm going to get here is I'm getting bigger and bigger numbers in the denominator. So my fractions are actually going to get close to 0, although they're never going to actually become negative. Well, that kind of makes sense because you should remember that the exponential functions have a horizontal asymptote at y equals 0. So that means on the left side, the graph gets really, really close to 0, although it does not cross. So something like that. So there's my graph of the exponential function y equals e to the x. So let's see, I could fill in a couple other things. The domain, all real numbers. The range, 0 to infinity. So what about my logarithmic function? So if you will remember, the log functions, these are the inverses of the exponentials. Okay, so you might remember when you see natural log, you should remember the basic shape I'm looking for is something like that. But actually the simplest way to graph this one is going to be, let me set up a coordinate plane again. Where did my ruler go? What happened there? Where were we? Right here. Let me put my ruler in here again. I was trying to line that up there, say. So it'd be something like that. Okay, so what I was thinking is, well, remember the log function ln of x is the inverse of the exponential function e to the x. So what if I just take my points on the previous graph here and I reverse the x's and y's? Okay, so what are my new points going to be? I guess I'm going to have a point at, let's start on the left, I guess. So 1 over e negative 1. So that's approximately a third negative 1. Somewhere here. Next one would be 1, 0, right? Okay, and then 1e would be how did I set this up? So 1e would be reversed. So let me go back here for a second. So 1e would be reversed, and it would now be at e1, which is about 2.71. So right about here, E1. Okay, now notice again that the exponential function has that horizontal asymptote at 0, y equals 0. So if I reverse x and y, then my log function actually has a horizontal asymptote, or a vertical asymptote rather, at x equals 0. Okay, so what is this guy going to look like? Something like that. And so that guy's domain would be 0 to infinity. Its range would be all real numbers. Now, using these two as base graphs, you could really do all different kinds of transformations. So, I mean, just as like a side note, like if you had something like this, you have an exponential function, and then you know it's shifted left 2. Okay, like if you have something like this, it's an exponential function, but make the x's negative, it's reflected, right? Let's see, need to write something. Reflect. If I have negative 2 e to the x, well, then I have an exponential function. The whole thing becomes negative. So the y becomes negative. Then I multiply the y's by 2. So that one I really have two things. I have reflect over the x-axis, and then I have a vertical stretch. So overall, I would have to take the points on the graph of e to the x, and then I'd have to multiply all the y's by negative 2. And you could do something similar with like, ln. If I had something like that, I'd take the ln graph and then I'd shift it up 2. If I had something like that, this is the tricky one. I'd take the ln graph, but then this guy's affecting the x. So remember, x things are opposite of how they look. So instead of multiplying the x by 2, I'd actually be dividing it by 2. So this would be a horizontal compression. I'd take all the x values and divide them by 2, etc. And you can apply all the same transformations that you learned in the algebra class.